Hello everyone, today we are diving into one of the most mind-bending discoveries in modern astronomy. A star that doesn't just orbit a black hole, but screams around it at nearly 1/10 the speed of light. This is S4714, the fastest star ever observed in the Milky Way, a cosmic speed demon locked in a death-defying dance with Sagittarius A, multiplied by the 4 million solar mass, supermassive black hole that anchors our entire galaxy. For decades, astronomers have stared into the dense, chaotic heart of the Milky Way, piecing together the lives of stars that dare to venture too close to the point of no return. For years, the star S2 was the crown jewel of these observations, a bright blue star that looped close to Squeezar, a multiplied by, and let scientists test Einstein's general relativity in the most extreme gravitational field we can access. Then came S62, which edged closer and moved faster than S2, breaking records we thought would stand for a generation. But nothing prepared us for S4714A, star that redefines what we thought was possible for a stable orbit around a supermassive black hole. Let S start with the numbers that will make your jaw drop. At its closest approach to Sagittarius, A multiplied by, called its pericenter, S4714, reaches a velocity of 24,000 kilometers every single second. To put that in perspective, light travels at roughly 300,000 kilometers per second, so this star is moving at 8% the speed of light, a speed so extreme that it could travel from Earth to the Moon in less than half a second. Our Sun orbits the galactic center at a leisurely 220 kilometers per second, taking 250 million years to complete one full lap. S4714, it zips around SGR, A multiplied by, in just 12 years. That is not a typo. A star that spends most of its orbit far from the black hole, then dives inward at nearly light speed, only to slingshot back out into the darkness. What makes this even more extraordinary is the shape of its orbit. S4714 has an orbital eccentricity of 0.985, a value so close to 1 that its path is less of an ellipse and more of a stretched, narrow oval, one of the most eccentric stable orbits ever measured around a supermassive black hole. For comparison, a perfectly circular orbit has an eccentricity of 0, and Pluto's eccentric orbit around the Sun is just 0.248. At its farthest point, S4714 drifts roughly 250 billion kilometers from SERA, multiplied by, but at pericenter, it skims just 12.6 astronomical units away, about the same distance Saturn sits from our Sunday. Imagine a star racing past a 4 million solar mass black hole, at a distance we consider normal in our own solar system, and not getting torn apart. That, the miracle of S4714. This discovery didn't happen by accident. It came from decades of patient, cutting-edge observations, led by a team of astrophysicists from the University of Cologne in Germany, led by Dr. Florian Paker and Professor Andreas Eckart. They used the European Southern Observatory's Very Large Telescope, or VLT, perched high in the Atacama Desert in Chile, one of the most powerful ground-based observatories on Earth. The galactic center is shrouded in thick dust clouds that block visible light, so astronomers rely on infrared instruments to peer through the haze and track the faint, fast-moving stars near Squeezar, a multiplied by. For years, the S cluster, a dense group of stars huddled around the supermassive black hole, was thought to have only a handful of members. But advanced imaging and data processing techniques revealed 5 new stars: S4711, S4712, S4713, S4714, and S4715, named after the famous German perfume 4711, as a fun nod to their discoverer's hometown. Among these, S4711 holds the record for the shortest orbital period, circling SERA, multiplied by, in just 7.6 years, but it never gets as close or as fast as S4714. S4714 is in a league of its own. Now, you might be wondering, how does a star survive this kind of gravitational brutality? The tidal forces near a supermassive black hole are strong enough to rip planets, stars, and entire solar systems to shreds. Yet, S4714 not only survives, but thrives in this environment. The answer lies in its speed and its orbit. Because it moves so quickly at pericenter, it spends only a tiny fraction of its 12-year orbit in the most intense gravitational grip of CRA, multiplied by. It has like a daredevil biker, speeding through a loop, the loop too fast to be pulled down by the force trying to grab it. But there's more to this story than just survival. S4714 is giving astronomers the first real-world evidence for a theoretical type of star called a Squeezar. First proposed nearly 20 years ago by astrophysicists Tal Alexander and Mark Morris, Squeezars are stars on extremely eccentric orbits around supermassive black holes. Every time they pass close to the black hole, the intense tidal forces stretch and compress the star, converting orbital energy into heat. This heat makes the star shine brighter than it normally would, creating a unique cosmic signature. Before S4714, Squeezars were just equations and computer models. Now we have a real star that fits every prediction of this strange class of objects. Every close pass-by, SQRA, multiplied by squeezes, S4714, like a cosmic stress ball, heating its outer layers and altering its brightness in ways we can measure with our most sensitive telescopes. This isn't just cool space trivia, it is revolutionary science. S4714 is turning theoretical astrophysics into observable reality right before our eyes. Let's talk about relativity, because this star is a perfect laboratory for Einstein's greatest theory. General relativity tells us that gravity warps space and time, and the stronger the gravity, the more extreme the warping. Near SQRA, multiplied by time, runs slower than it does on Earth, and the fabric of space itself is bent into a near spiral around the black hole. Stars orbiting in this warped space don't follow simple elliptical paths like planets in our solar system. Their orbits precess, meaning the entire oval shifts slightly with every loop, tracing a shape like a flower petal over time. S2 gave us our first clear proof of this effect near a supermassive black hole, but S4714 is taking this test to a new level. Its extreme speed and close approach mean relativistic effects are far more pronounced, allowing scientists to measure tiny deviations in its orbit that confirm Einstein's equations with unprecedented precision. Every time we track S4714 around the black hole, we not just watching a star move, we watching the laws of physics operate at their most extreme. This star is also rewriting our understanding of how stars form and evolve near supermassive black holes. For a long time, astronomers thought the area immediately around SQA multiplied by was too violent and chaotic for stars to form. The intense radiation and gravitational forces should have blown away the gas clouds needed to birth new stars. Yet here, we have S4714 and its four sibling stars, young hot blue, B-type stars, that clearly formed in the last 100 million years, relatively recent in cosmic time. This means our models of star formation in extreme galactic environments were incomplete. S4714 is forcing us to rethink how stars can be born, survive, and evolve in the shadow of a black hole that could destroy them at any moment. It also raises a thrilling question: how many more extreme stars are hiding in the galactic center? The team that discovered S4714 believes this is just the beginning. The VLT and upcoming telescopes, like the Extremely Large Telescope, or ELT, will have even sharper vision and can detect fainter, faster stars, even closer to SGR, multiplied by. We might find stars moving at 10% the speed of light, or even closer to the event horizon, pushing the boundaries of stable orbits to their absolute limit. Think about the scale of this achievement. We're sitting on a small planet, orbiting an average star, 26,000 light-years away from the galactic center. We've built machines that can see through dust, measure speeds that defy imagination, and track stars that complete orbits in a human lifetime. S4714 isn't just a record-breaking star. It is a testament to human curiosity and ingenuity. It has a reminder that the universe is full of wonders we haven't even dreamed of yet, waiting for us to point our telescopes upward and look. Let's recap what makes S4714 so special. It is the fastest known star in the Milky Way, hitting 8% the speed of light at pericenter. It has one of the most eccentric orbits ever recorded around a supermassive black hole at 0.985. It is the first confirmed Squeezar, a star heated and compressed by black hole tidal forces. It is a perfect test for general relativity, proving Einstein right in the harshest environment imaginable. And it's rewriting the rules of star formation near the most dangerous object in our galaxy. Every time we learn something new about S4714, we learn something new about the universe itself. We learn about gravity, about time, about how stars live and die, and about the forces that shape entire galaxies. Sagittarius A, multiplied by, is more than just a black hole. It is the heart of the Milky Way, and S4714 is the fastest pulse in that cosmic heart. As we continue to study this incredible star, we'll unlock secrets that will shape astronomy for decades to come. We'll refine our theories of relativity, improve our models of black hole environments, and maybe even find signs of other exotic objects lurking near the galactic center. The story of S4714 is far from over. It has a story of speed, survival, and scientific discovery that connects our tiny world to the grandest scales of the cosmos. It has a story that reminds us why we look up at the night sky, why we build telescopes, and why we never stop asking, what if? The universe is vast, mysterious, and full of objects that challenge everything we know. And right now, at the center of our galaxy, S4714 is racing through the darkness, carrying the answers to some of the biggest questions in astrophysics. Please like, comment, share, and subscribe to the channel